Record recording in progress. So, we approached the last lecture that any analytic function can be expanded in Taylor series, and if function has some singularities, then it can be expanded in the Laurent series. As I told you, should remember formulas and this scheme, how we arrive from one to another. So how we get expansion of analytical function into series? The starting point is the Cauchy integral representation. So this formula that any function fz can be represented in this way, How we, if you go to the scheme, how we approach this formula? The beginning was Cauchy-Riemann condition. Cauchy-Riemann condition and infinite differentiability was definition of analytic function. Then, by using green formula, we prove that function integral of analytic function over closed contour is zero if and only if it satisfies Cauchy-Riemann conditions. So, in fact, in green formula, there is Cauchy-Riemann conditions. After this, by using the Cauchy integral of analytic function over closed contour is zero, we prove this formula by taking here we have singularity, here we have singularity. Yeah, okay, so the analytic expansion is going from this formula. Now, maybe go back to this picture, In this picture, we have the point Z0. This is the point of singularity. Outside of this point, our function is analytic. Then we take any point in this circle, and here would play a role the radius of the circle and the distance from point Z to Z0, from Z to Z0. Yeah, so now in this integral, this thing W minus W, variable W is here on the circle. We integrate here counterclockwise, always counterclockwise. Now this expression, this point here on contour and point Z, so this, we shall represent in the following way. We subtract the center of the circle and at the center of the circle. So this delta is Z minus Z0. So the picture is this one. So it was center. Here we integrate over this. So there is W minus Z0. And here we have this point Z and this distance from this point to the center. Now, the second part of the expansion of function into series is geometric progression. So in this theorem, only 2 points. First, Cauchy integral representation, and second, geometric progression. So we want to have, what is our aim? Our aim is to reduce everything to this, to geometric progression with t less than 1. T is now complex, but the proof is the same. Proof is totally the same as for real. And now we consider this inequality. So we know that this distance is less than this distance. That's all. So this is geometric progression is here. That Z is inside circle and W is on the boundary. So the distance from the boundary to the center, of course, is larger than this distance. So this is less than 1. So we can write this directly, Z minus Z0 divided by W minus Z0 is less than 1. So this number, this complex number, can be used for geometric progression. So now we have this, and now we would like to use this as the sum of geometric progression. No, by some reason, this is 1 over t. No, the only thing that there is not 1, but we can take this out, and then we get this. So introduce this t, and as I thought, we write this in this way, and then use geometric progression. So this is very elementary. So when we approached Cauchy integral representation, then we can expand our analytic function as power series, and this is power series because this is Z minus Z0. By using geometric progression, nothing more, nothing more. So we prove this formula, and yeah, so this is expansion of any analytic function in the power series. Where this expansion work? It work everywhere in the largest circle where function is analytic. So how to find the radius of convergence? We take Z0 and look for other singularities and measure the distance to the closest singularity. And here our function is analytic. So this formula is very similar. Cauchy integral representation plus geometric progression. So if you get on your exam question, give me the schematic derivation of the expansion of analytic function in the Taylor series, more or less you write Cauchy formula, you tell that we have geometric progression and that this denominator can be represented in this way. So that's all. Go to more complex situation. Convergence, convergence I already told. Let Z1 denote the singularity outside of contour, which is nearest to Z0. So the largest circle around Z0 without singularities. Yeah, so to find the radius of convergence at Z0, find the nearest point. So there's this nearest point, and then it would converge for all Z minus Z0, which are less, strictly less, than Z0 minus Z1. Now they consider examples. No, the simplest example is just this, the sum of geometric progression. No, they calculated derivatives. They want to expand, it's not in the point Z, but in the point Z0, 1, minus 4. They calculated derivatives in this point and wrote this series. But of course, it's more natural just again write Z minus 1, 4 plus 1, 4, and then you will get the same answer. Yeah. So how to do this? You need Z minus 1, 4. So write minus Z minus 1, 4, but you also should add it, and it would be this 3 divided by 4 appear on this place. Yeah, appear at this place. Okay, so now we go further. Exponent. It's more or less evident at the point Z0. We can write in this way because we know its derivatives. There is no singularity, so this function has no singularity, so the series converges on the whole plane. This is so-called entire analytic function. Yeah, so sinus, the same story. Cosinus is the same story. And what is useful, what you can use in many applications, you can do it in usual analysis. Yeah. So if, for example, Z is small, Z square is essentially less than Z, and you can approximately write exponent in the degree Z, it's 1 plus Z. Cosinus 1 minus Z square divided by 2, sinus Z approximately Z. It is very convenient. To do this. Now we repeat about Laurent series. Look here, it's also the same formula, but here we cannot integrate, here we should take away this point Z0. So we take two circles, this circle inside this ring with hole. Our function is analytic. So we can use this formula, but see all this complex contour, yeah? All this complex contour. Then as usual, we go this whole to 0, this integral down, integral up disappear. And then we have that this integral is the sum of the integrals of this one and this one. But now they have different directions. If we change direction, we get minus. So this is minus. And then we have two integrals. One integral is over large contour. Another integral is over small contour. We make the same trick. On the large contour, we did as before and get expansion with positive degrees of z. On the small, we do other way around. So we take, so this is small contour. Here, this denominator is larger than nominator. So, and then we get expansion on this final expansion into Laurent series. Final expansion into Laurent series would be this sum. So Fz is equal to this. So maybe this formula should be, you would be able to write it. And delta is here z minus z0 in the degree n. But now degrees go from minus infinity to plus infinity. So in Laurent series, you have terms 1 divided by z minus z0 in first degree, in second degree, and so on. And so on. Yeah, what is important remark? So coefficients are given by these integrals. Coefficients of Laurent series given by this integral. What is important remark? In Taylor series, for n equals 0, 1, and so on, these coefficients were given as in your course of usual mathematical analysis. Derivative of degree n divided by n factorial. Derivative of degree n divided by n factorial. Here it does not work. How to see that this formula does not work? Because, for example, n equals 0. Not derivative, but coefficients a0, the constant. Our function has singularity in the point z0, so it would be infinity. So this coefficient is not equal the value of function in this point. So even for positive n, these coefficients of Laurent series is given only by these integrals. They are not given by derivatives. So even n and 2 equal 2 and so on. So this is final formula. This is final formula for Laurent series. Yeah. The only difference from Taylor is that from minus infinity to infinity. Yeah. The difference is that Taylor converges to, within the circle. It is more or less the same story, but the series does not converge in the point z0. So it is the same story. So we find the maximal circle around z0, but in the point z0, the circle does not converge. So in the point z0, this circle does not converge. If function is analytic, look who are these terms, coefficients for negative degrees. So the idea is that now let us apply a Laurent series for analytic function. It is clear that we should get Taylor series. We should prove that these coefficients corresponding to negative degrees are 0. No, it is clear why. So that these coefficients, if degrees are negative, they are given by this. So this is in nominator. If degrees are positive, this is in denominator. So if they are positive, we get this formula, which was for analytic functions. If they are negative, it is 0, because this function now is analytic. This function now is analytic. So this will be cancelled. Now we go to, it was very general theory, any singularity. But typically in your life, even in applications, you always meet pole. The denominator is 0, nominator is not 0, or the 0 of denominator is higher than 0 of nominator. Yeah. So now we consider our function, which has not only singularity in the point z0, but the pole of order m. Now we see by the same reason. So write these coefficients, and these functions are analytic. So they are 0 for all this. So check that this is analytic, because m plus l minus 1 is non-negative, yeah? And then they are 0. So finally, if function has the pole of order m, it is written in this way. So it is Taylor series, it's analytic part, plus this part with singularities, and pole of the degree m appears with this denominator. So Paul, I think he is misprint somewhere. It should be not W, it should be Z. So in the formula 432, in denominator, you should write not W variable, but Z, this variable function. So here is Z, here is Z, here is Z. So for example, if the polo has degree just 1, it would be only this term. Only this term. And what is the meaning of this coefficient? This is precisely residue. So in principle, typically, we would be interested not in the whole this singular part of Laurent series, but only in this term, to find residue. So one of the ways to find residue, because how we find residue? We multiply our function by z minus z0 and take the limit, and we get this, for pole of degree 1. Okay, so now we can consider this non-singular part. This is analytic function. You can denote this by phi z. So this is each function with singularity has 2 blocks. One block is positive degrees of z. So this is analytic function. If pole has degree m, it has also singular part, and this singular part has this simple form, Consider examples, and so, for example, they consider function zn 1 over z. This is this is essential singularity. It is not a pole, because if we multiply this for any z, it would not go to 0. Any degree of z, this function is very bad. Exponent 1 divided by z. It is not pole, it is essential singularity. So how we do? We expand this function, we expand the exponent in the degree z, put 1 over z, and multiply by zn. So we get this series, So here should be n minus k. It is misprint. It's not equal to k, but n minus k. It is misprint. And now they change the order, and they get this expansion. So here we have that regular part, analytic part is polynomial, but there are infinitely many negative degrees, Sinus z not divided by zn. No, it is more or less no expansion for sinus divided by zn. We just subtract n. We get this formula. This paragraph 4.3 we shall not use. So it is very technical criterion how to find radius of convergence. No, for elementary functions we never use it. We go just to the next paragraph. Radius of convergence, Kashi. Yeah. No, this we never shall do. Limit, arithmetic. No, this is more or less evident. For example, if you have two Laurent series, and we want to find the sum, no, you do this as you do, you write the sum, and coefficients would be given by the sum of coefficients. Here, for example, the sum of two Laurent series are given by this formula. Addition and subtraction. No, this is more or less this expand, and then multiplication is worse. You just multiply them formally. But what is the problem? If you multiply formally this sum by this sum, it will be this expression. But this k plus L can equal to n for many combinations k and L. So z minus z0 in the degree n would be all these guys which have this which sum is equal to n, which sum is equal to n. So no, it can be written even in this form. No, we never will use this general formula, but if you have two concrete functions, you can of course multiply them. Division, multiplication of two power series, no, you can multiply them, open brackets and so on, and then collect everybody with the same degree. A division is more complicated. We shall not do this. We shall not do this. And now we go to, now we go to interesting thing, which will be important part, This is residues and for the pole of order m, Yeah. So as we know, if the pole has the order m, our function is expanded in the Laurent series. So one block is analytic. It's not interested for us. So when we speak about residues, analytic block for us has no interest. For us, it's interesting only this block, So this function is analytic. We can forget about it. So when we integrate, so we want to find the integral of function which has pole of degree m. Before we worked mainly with functions of the pole of degree 1. Now pole has degree m. So we just integrate this representation, integrate this. We want to integrate fz dz. So we integrate this. This integral is 0 because it's analytic. Integral of analytic function is always 0. This we have over everything. Then we have this, okay, so this integral is 0. So now our integral has this form. Now they do the usual integration. So this is integration of over the circle of radius rho around z minus point z0. So they have this parameterization that z minus z0 is equal rho, and here is this angle around circle. Now we have differential. It is as it should be done. It's constant disappear rho I exponent d phi. So now we put into this integral. So this is nothing more special. So now it's usual integral. From, no, we always can write from 0 to pi. No, this phi 0 is not so important. We can write always from 0 to 2 pi. And we have this exponent. If this thing is not 0, then this, L minus, here is this term, L minus 1. So it depends whether L minus 1 is 0 or not 0. So if it is not 0, this integral is 0. So the only term which give us something, would be when L is equal 1. So L equal 1 means who is L equal 1? L equal 1, it is this term. So the only term in the, so the function can be very complicated, yeah? But the only term which will give us something to integral is this one, So in this sum, will survive only L equal 1, So all other disappear. So this should be memorized. Somewhere. That the only thing which contribute is z minus z0. So the only term which contribute to, and we can change our function as we want beside of this term. So here, for example, I can put some another big analytic function. Here I can put also different degrees, but still pole. Essential singularity would not work. An integral would not be changed. The integral is here. Integral is only here. And then we get this formula. Finally, we get the formula which we use for the pole of degree 1. Now it is for pole of arbitrary degree m. that integral fz dz is equal to pi, and this coefficient, which is in our series, this coefficient give us this integral. And we can call this, no, before when the pole was simple or pole of degree 1, we know this, that this coefficient was equal to residue, and residue was defined in this way. Now we define residue for any pole just as this coefficient. So this is important point because we define residue in 2 steps, which is pedagogically maybe not good. So, but it's again the line represent your knowledge by portions. First, they considered the pole of degree 1 and determine the residue by the formula 4,112. So it was definition before. But we can calculate, if you multiply our function fz by z minus z0, we will get this answer. We will get this answer for the pole of degree 1, and we get this coefficient. So roughly speaking, all business of this integration is around this term. The term in the expansion of our function in Laurent series with respect to z minus z0, It is, you can suspect that it is unexpectedly simplification of calculation of integral. So function can be very complex. For example, if you start, if you from the very beginning, without knowing this formula, try to make parameterization in all these terms. So it would be very long calculation. But you see now that it is only this term which play the role, So very complex integrals can be calculated by extracting this form. Now we want to study the methods, and this would be more or less what you will get on your pre-exam and exam. Yeah, how to calculate integrals. And for calculation of integrals, you should be able to calculate residues or this coefficient, a minus 1 z0. There are 3 different methods. 3 different methods how calculate this coefficient. First one is called direct Laurent expansion. So just you should expand this function. Sometimes it's very easy. Expand this function in Laurent series and find this number. So it is, but sometimes it's not so easy. The second method is derivative method. So we might suppose this is we work in the situation when we have the pole of finite degree, finite degree m, pole of finite degree m. We multiply our function by this maximal degree, which is in denominator. We want to destroy denominator, So we multiply it by this, and we get this polynomial, this coming from negative degrees. This star is multiplication. Then we multiply z minus z0 m, this analytic function. And we want to find this coefficient. If you just try to take limit, as it was before for the pole of degree 1, it would not work. So it would not work, because this would go to 0. So we should make something that this z minus z0 in the degree m minus 1 would disappear. How disappear monomial? By differentiation. So this function, we should find its derivative of degree m minus 1. Then all these guys disappear. This would be just constant. And here we still will have z minus z0, at least in the degree 1. So this would also disappear. So the second method, how to find this residue or coefficient for first negative degree, is this formula. Either you can memorize or you can derive. Derivation is one line. This function, which was general Laurent expansion, then you want that all these negative degrees would disappear. You are interested only in this. So you multiply by this degree of z minus z0, and then you want that other terms would disappear, that only these terms survive. So you take derivative of degree m minus 1. So it will appear m minus 1 factorial, you will divide by them, and this formula. Yeah, we shall use it during this lecture for training. Yeah, derivative method, Paul defined it. Yeah. No, they now consider this situation. It is more or less typical in all examples. Suppose that we extracted this pole. So suppose that denominator is z minus z0 in the degree m. And in numerator is some analytic function. So if we start to integrate, we shall use this formula. And this m, which was in denominator, and this disappear, and we get this formula. So it would be just this. Yeah. Ratio method. This method sometimes, this methods work when we have, for example, two analytical functions, one and in denominator another, and in the point z0, this function has 0, and this function has 0, and maybe zeros of some degree. For example, this function is z minus z0, and this function z minus z0 square. So then it is very easy to find the pole. So this we don't need or large. No, it's good thing. But what we have? Suppose that function which is who was r. It was function in nominator. Suppose that function in nominator has 0 of the degree m. So the rz0 is 0, derivative is 0, and derivative of degree m minus 1 is also 0. So suppose that, no, for example, it is just z minus z0 in the degree m minus 1, yeah? And this is non-zero. Suppose that denominator has 0 of higher order, of order m plus 1, Then what they do, then we expand into Taylor series nominator, and there is this term, and denominator, he is 1 degree larger. So if we now cancel them, we get this formula. So this formula to calculate residue or coefficient of degree minus 1, it is given, we differentiate how many times nominator, as many times as is the degree of 0. So the degree of 0 was m, to get non-zero number. And we differentiate denominator as many times to get here non-zero number, because we ask that this is in nominator has order of degree m plus 1. So this is formula. When it works not so often, but you will have tasks sometimes. But task would be precisely for this situation. It works very good when denominator is non-zero and nominator is 0, but already derivative is not 0. So then this formula is just value in nominator divided by derivative of denominator. So here m is 0, and this is first degree is 1. What they want to tell that if the degrees of zeros are higher, for 2 it still work, but if they are high, it does not work. So because for 2 is already this formula, no, we shall never use it even for 2. This third method, the method when our function is fraction of two functions and both have zeros, it works very well only in one case, when nominator is non-zero and denominator is 0, but the first degree is non-zero. more or less as denominator has form some constant z minus z0. Here it works very well, but no, it can be used, but formula becomes more and more complicated. So already here we need to find the second derivative, the third derivative. So we should never use this, we shall never use this formula. Okay, now let's consider examples. Let us consider examples. Let us consider examples. For example, this function exponent z plus 2 square. Of course, it has, because this function is analytic, it has no singularities. Moreover, this, for example, is considered the point z equals 0. Moreover, singularity is only here, so the whole, this fraction, so it is very good to extract this non-singular part. So non-singular part is exponent z divided by z plus 2 square in the point z0. So how we can find, for example, residue? We check three methods. Yeah. And the second point is this, that there are two different points and there are two different residues. Yeah. We check method 1 by direct expansion for both points. So start with point z0. So it's the pole of degree 1. We expand this function. In the Taylor series. We expand this function. This is all these things can be expanded by using geometric progression. And then we multiply them. I think here this method is not the best. When you will get the task to find residue, you should select between these three methods. Here you should multiply series. And you find this direct Lorentz expansion. So residue is 1/4. But I don't like this method because in fact, you even cannot. So here use progression. You even cannot use progression. I think you should use binomial expansion. Yeah, so it would be 1z divided by 2 in the degree minus 2. So they use binomial expansion. So it is okay. We can do this, but it's direct is not so good. So now we go to point minus 2. Here we expand this in exponent. We expand in this way. So we write z plus 2 minus 2. So it would be exponent in the degree minus 2. And here is expansion of exponent. Then we take this function 1/z, and we also should expand it in the point minus 2. So you should learn, this is trivial, yeah? But you shouldn't learn this technique. That this function 1/z, and we should expand it in another point. So that 0 is not 0. It is another point. In this case, z equal minus 2. So what we do to this z, we write +1, +2, -2, and we finally get this sum of geometric progression. We expand it into series. And now we should again multiply this series. And finally, this coefficient over this degree 1 divided by z2 plus 2, it is this one. So this is residue. I think here, at least in the point z equals 0, it is pole of degree 1. It would be easier to calculate residue by derivative method. So this is the pole of degree 1. We just multiply by z our function. So z and z cancel each other, and limit z equal to 0, 1/4. So here it's very trivial. When z equal -2, it is pole of degree 2. What we do? We take our function, multiply by this square, so that this, to which degree multiply, it's clear that this singularity should disappear. So the same degree as this singularity. And then we should take derivative of degree 1. So the pole, if pole has degree m, derivative has degree m minus 1. So for the pole of degree 2, the formula is simple. So if you have the pole of degree 1 or 2, I think the easiest way is apply derivative method. So pole degree 1 or 2, the easiest way is, well, sometimes, of course, you can easily expand into, for example, if our function would be just, without exponent, then direct expansion would be simple. It would be simple, and we can do this by direct expansion in the Laurent series. Now we should apply the third method. The third method is following. We should have our function as fraction. This is numerator, pz, and this is denominator, and this is denominator. But I think it's better to choose this. So this function still has no zero in the point z equals 0. In the point equals 0, we select this as numerator, and we divide by this. So this block is numerator and this denominator. So the pole of degree 1, so this is not 0, and this is, we just multiply by it. So it is our answer is this value of this function in the point 0, and when was the pole of degree 1, it is just first derivative. Somewhere we had this formula. For this. So this formula. Maybe it's good to memorize this formula so that if it's pole of degree 1, we just put 0 as z0 in numerator and divide to the first degree. Okay, so these are all these methods. This we consider it. Ratio method. Problems. Okay, so we finished this chapter. Now we want to apply complex analysis to calculation of very complicated integrals over real axis. It could be looked as very strange activity, but it's not so strange. As you have seen, when we calculate integral of complex function, more or less we take away everything beside one term, a minus 1 divided by z minus z0. So this function, which can be on real line very complicated, and we should make summation over all x of very, very complicated expression. When we go to complex plane, of course, we should extend our analytical continuation. We should not for any function it works. So not any function can be expanded in the series, But for those functions, for example, z, x, and so on, we can expand it into analytically into complex plane, and then we can calculate integrals over closed curves. This integral is 0. But we don't need integral over contour in complex plane. We need integral over real line. What we shall do? We consider, for example, integral over real line can be considered as integral when we take finite interval from minus r to r. Then we integrate over this. We make this contour. So the integral over closed contour can be calculated. It can be calculated. We should find all singularities inside this contour. We can go even this way. It is also the same formula, but we should find singularities inside this contour. But we have also this thing. this thing which is not so nice. We need only this block. We need only this block. But here is also integral over half circle. This half circle or this half circle. We don't need them. This method would work. This method would work when this integral is equal to 0. When this integral is equal to 0. So what is the idea? What is general scheme? We want to calculate this integral. We expand our function fx if it's possible. It's possible, not always. It depends on the form of this. It depends on the form of this. It depends on the form of this function. We expand it to the complex plane. In the complex plane, we cut integral over whole real line to integral over segment minus r to r, and in some way close this integral to make the closed contour in the complex plane. This integral is 0 if function is analytic. If it's not analytic, it's just the sum of residues inside this contour. But what is bad? We do not need this, and or this. So these guys are not of interest for us. We want, and we shall define the class of such functions that this integral is 0. This integral is 0. Main remark, that it's not enough that function is go to 0. So if function f z approach to 0, for example, is go very quickly to 0 on this half circle, it does not imply that this integral is 0. So we should find conditions on fz that this integral go to 0, as I told, fast enough. We shall do this as usual by coming to polar coordinates. So this is half circle. Here would be usual coordinates, and here would be polar coordinates. So this is on this. In fact, we are not more interested in this thing. This thing is given by what we are looking for. We are looking for this. We are looking for this part. So we are interested in the integral over this half circle. And we want to find condition when it goes to 0, when radius goes to infinity. When it can look strange, does it? It's larger and larger contour becoming very big. But we want that it would go to 0. It means that the length of the contour should increase not as quick as function decrease. So function should decrease quicker. So we change as usual on half contour, we make exchange of variables. We get this. Now it is from 0 to pi because we have only half circle. Typically it was from 0 to 2 pi. Now it's 2 pi. And we get this, integral. No, they consider both cases. Why they make two pictures? Why there is not enough to consider only this? Sometimes function decrease in upper half plane, sometimes in low half plane. So, and you should get understanding which integral to take. So if function decrease here, you take this integral. Well, very quickly it should decrease. If you see that here function does not decrease or decrease not quickly, you take this integral. Therefore, they consider both. This is counterclockwise, and this is, because in both cases we want this integral. Dx is this. So, and this is clockwise. So therefore, they write both formulas. For this, it's plus, for this minus, or yeah, for this plus, for this minus. So they change variables. This is upper half plane, and this is lower half plane. Yeah. So what they want, first of all, what we see this guy. This is on the unit circle. So exponent I phi is always has absolute value 1. So we are not interested in this. We're coming we're coming that our length of half circle is increasing. It is here in this R. This R is the radius of our circle. So this is go to infinity. So this, our function on this half circle should go to 0 quicker than this R, than this R, than this R. Yeah, this we can forget about it. Yeah, so now we have this, and this is what they want to tell, that since our function is continuous, our function is continuous, its value on this circle, on this half circle, in fact half circle, it is more or less as this R, because the length is now pi. We can forget about pi, it's not, it's constant. So here is this R, radius, and here we have our function on the circle, our function on the circle. So this is, we can write FR, FR. The symbol equivalence means that it is approximately equal. So this integral of the half circle would go to 0 if our function, if we put it inside it's the real number R, and if you put it R, is go to 0. So this is definition what it means that our function go to 0 sufficiently quickly. That our function go to 0 sufficiently quickly. So then, yes, then this integral would be given plus 2. No, for example, if you go up a circle, if you take up a circle, it would be 2pi, and there is the sum of residues inside, of residues in singular points inside this upper circle, Of course, if function f is real, you, to check whether your answer is correct, you should get real number. Because here is, we go to complex plane, we make calculations in complex plane, we get answer in this form, but answer should be real. Answer should be real, so this residue should be contain imaginary part. So this I should disappear. If your integral over real line would have imaginary block, it's something wrong, something wrong. So also here is I, it should be compensated by I here. Finally, it should be no I. It should be no I. So this is the most powerful method of calculation of integrals over real line of very, very complicated functions. We shall consider examples a bit later. But the idea, maybe it would be even such question. Why analytical continuation to the complex plane can simplify calculation of real integrals? Because, as I told, in the complex integral, only the whole function is not important. Only one term, a minus 1 divided by z minus z0 is important. So by going to complex plane, we can ignore by very complex part of our function. On real line, we cannot ignore. We should integrate, take any point, value of function in this point, and make summation. So the simplicity was far long before. The simplicity was, I point to this. Yeah. So the simplicity of this method was, I think, here. The simplicity of this method is here. Such function, if you expand it into Laurent series, it can be what you want here and what you want here, and all these parts are in this fx on the real line. If you put instead of z a real number, but integral is only this number. So integral is only this number. In fact, we integrate only this in complex plane. Yeah, so this was this method of calculation of integrals over real line. Evaluation of these integrals. So the idea is very simple. And finally, whether you can apply this method, you should check only this condition, to check only this condition. If this condition work, then integral over this goes to 0. So the length is p pi r, but function should decrease quicker, and make this integral going to 0. So now we can make a break. Maybe 10 minutes. 10 minutes, and then I want to consider some examples, more or less exercises. So, okay, so 10 minutes break. Yeah?
Det är lite kul faktiskt att det är liksom att man använder saker som man redan har använt. Den ska vi använda här. Ja, det var liksom som jag kände. Men nu kom det liksom, vilket jag är jätteglad av. Jo. Och då känner man liksom att man har lärt sig något som man har nytta av. Jo. Det är samma när jag ser typ i komplexen som jag ser tillämpningar från grupp till och vet aldrig vad det var för spännande på det sättet. Enhetsrätt psykisk grupp som rörelser på multiplikation av komplexet. Och det är sånt som jag tror. Det var det han sökte säga för föreläst. Och så. Det var roligare så skriva på tavlan. Ja, det hade varit mycket lättare om ingen namn hade skrivit på tavlan. Det brukar gå lite långsamt. Och så går ju helvete som vi gjort ett liksom av Mattias. De hade ju också inbyggd och spela in samtidigt som de skrev. Det tyckte jag var riktigt bra liksom. Ja, jag gillar Mattias som bara satt där och spelade fram och började spela in och sen körde han på liksom. Jag älskade Mattias liksom att han hade så här repetition för Johan.
För det är ju bara ett.
Skrivningar är jättebra. Snyggt också, bilder och olika färger. Så de lila och orange jag kan fortfarande inte släppa det där som han kör dem färger. Jag gillar det. Alltså det var en standardstart för en röd då. Jag märker att jag antecknar inte. Man är inte riktigt antecknar faktiskt. Sen så har jag skrivit block när jag också. Jag har ju kvantmekanikstoppet. Och där har jag ju bara jag inga anteckningar heller. Utan vi har förinspelade föreläsningar. Och sen är det bara utblick på man. Men det är matematik. Jo, det är här. Så har du ju gamla. Det är mycket svårt på sådär standardvikelsen för den här kommer fram standardvikelsen för P. Det kommer för rörelsen. Den är det ju då. Men det är ju vår funktioner. Sen har vi en sån standard.
Ja, det är den stora.
Ja, det stora precis. Där som beror av, den är tidsberoende. Men vi försöker bara räkna med den tidsoberoende.
K1.
Sen har jag bara att man skriver en... Ja, det var ett litet hopp här. Det som är här uppe, det var på konstanter som vi upp som vi bara skulle använda. Sen här är det själva...
Och det är jätteenkelt. Ja, det är annars har vi gjort.
Vad var det här?
Jag skulle få familj där P som är 0. Jag glömde dock den udda funktion. Så ska man rätta att den är 0. Den udda då från minus en udda från grund. Så bara där, jag fick det till 0 där ändå. Men sen var det när man skulle ta fram milva för P kvadrat. Jag vill med jobba lite andra där det var.
Det borde inte vara något.
Det blev en slutade på resan i alla fall. Och det var rätt. Ja, det blev bara det blev fler.
So we open another file. Yeah. And we shade. So I would like to consider similar examples to find residues as was in lecture, more or less as kind of training, yeah? It's kind of training. So, okay. Laurent said, consider this function. This would be more or less standard function which you will get in your consideration. Quadratic polynomial, it's you always can find the roots of this polynomial. In this case, it's -1 and -2. So the picture is that you have the circle around -1 of radius 1 and around -2 of radius 2, because the distance between singularities is precisely 1. Now I would like to expand this into Laurent series. Of course, we can do this method of multiplication, what was done before, but exists another method. Maybe you have used it when you calculated integrals in the course of usual analysis. You can write this fraction in this form. So these are two factors, z plus 1 and z plus 2, and find these coefficients a and b. So you just go to common denominator, which is this one, and you get this equation. So, and you can represent this function in this way. So then it is very easy to find its residues, because in the point -1, this function is analytic. It has no singularities around -1. And this function is expanded with respect to, for example, Laurent series, and we get that residue is equal 1. So this is this coefficient. And residue in the point -2 is equal -1. So now if you want to calculate this integral, it would be 2 pi I residue, so 2 pi I. Yeah, so this is also good method, especially when you have quadratic polynomial in denominator. Quadratic polynomial in denominator is very simply works in this way. Z equal to, it's if you want to expand into the series, for example, if you have task not find only residue but expand into the series, for example, in the point -1, this is already, but here we should, instead of 1 plus 2 plus z, write in this form, so we get this expansion. So this method is not so bad. Especially if in denominator is quadratic polynomial. Now consider other methods. The method of derivatives. Yeah, the method of derivatives. So this formula, what we studied, if the pole of degree m, this normalization, degree m minus 1, multiplication z minus z naught in the degree m. In our case, both poles have order 1, and here the formula is very simple. It's just this limit without derivatives. So, and now we multiply by this. We get this, and this point 1. Now this, it is, yeah. Now we consider more interesting maybe function when the pole is of degree 2, If pole has degree 2, we multiply by its z minus z0 in its degree. So if pole has degree m, we multiply by z minus z0 in the degree m. Derivative of degree m minus 1 and normalization 1 minus m minus 1. Yeah. So this formula of this form, this disappear. So z plus 1 in square disappear. So it would be this, and it is expanded. Now we can, we can get from Laurent series immediately. Yeah, we get from Laurent series immediately. Now we apply this third method. Suppose our function is this fraction. Here should be in brackets. So then the formula is the following: if nominator has 0 of degree m and denominator 0 of degree m plus 1, so there is this formula. These are derivatives. So there is mistake. They should be in brackets. Derivative of degree m and m plus 1. So in our case, we consider this function, for example, in the point minus 1. So this function can be considered as nominator because it has, and this function is as denominator. So we should take this. It's no 0 at all. So it is just function by itself. And here is the degree of 0 is 1. The first derivative, it's equal to 1. So this is, yeah, so what you, of course, there can be very complex expressions and you can spend a lot of time, but what you at least should know how to apply 3 methods when in denominator is quadratic polynomial. So when in denominator is quadratic polynomial, you should be able to do this by this method as you like. So either this one, either with derivatives, or if it's pole of degree 1 or 2, by using this formula of this formula with derivatives. Yeah. Okay, so with this we finished, and then there was stop sharing. And there was also a question about one. I hope that we will see the on this screen. Can we write? Yeah, we can write. There was very simple question, but few people did not solve it home. And maybe we shall look how to solve this problem. Would they see this? I think they would see. So there was the problem of the following type. It's not clear whether it is seen by other people. Maybe we can move, maybe not. Yeah, it's seen. Yeah. Oh, good. So they have triangle. They have x, y, and triangle with points this P1. This point P2 in the I port, it was maybe 3I in this home task. And here is the point -3. So, and we should integrate over this triangle. And function, maybe it was a bit for people not usual. The function was over this triangle we want to integrate. Over this triangle. We want to integrate function exponent z minus z bar dz. Now, first of all, maybe some people were disappointed that this disappear. But of course, this analytic function, an integral over triangle of Ez dz is just zero. It's just zero. So we can forget about this. And in fact, there is integral minus z bar dz over triangle. I write z bar as typical. In your book, it is z star. And here maybe it's conjugate. We know that z conjugate is not analytic, so we expect that this integral is not zero. And how to be? We have no other choice than parameterize all part of this triangle. First, make parameter on this part, then make parameterization of this part, and make this. For circle, it's easy because circle is just one parameterization, but here each piece should be parameterized in its own way. So, for example, from P1 to P2, P2 part. Here, x is equal 0, now x. So we would like parameterize z. X is equal 0 here, and y has the form, for example, I, and here is 3t, and t from 1 to 0. So when t goes from 0 to 1, this z goes from this to this. This from this. Now we find dz. dz is very simple, it's dt. And whom we should integrate? We should integrate z bar equal on this minus 3it. So the integral is very simple. Where we write it. For example, here should be integral minus 3i. Let us write everything. So it was minus z bar minus 3i t. Here again 3i dt, and from 0 to 1. So that's all. It's a usual integral. So it is 9 minus 9 integral from 0 to 1 t dt, and you can calculate it. In the same way, you go from this is point P3, from P3 to P1. What is a bit more complicated? You should find equation of this straight line. Somewhere in gymnasium, I think, maybe in course 9, you was able to find equation of line which goes through 2 points. Yeah, if you have 2 points, we have points with coordinate 0, 3i, and point with coordinate minus 3, 0, and you should write equation of straight line in the form kx plus m, and you put first the first point, you get one equation, then you put the second point, you get second equation, you find k and m, and then in z you can take x, for example, as t, and y would be kt plus m, and z is t plus I by kt plus m. So you find this line, and then you integrate over this line. You find dz, and you put it in integral. So this is not so difficult, and maybe the main problem is only here how to find the equation of straight line which goes through 2 points. I precisely now a bit help to my daughter, and they precisely studied this in class 9 in the school. It's not even gymnasium, yeah? So you can recall. Because these integrals over triangles will be in your tasks. Yeah, so this now destroyed. Okay. Okay. So now we go back. Now we go back to our integrals. And again share. And we find our book where we were today. Yeah. Yeah. So we're back where we was at the end of the previous lecture. So we found the machinery to calculate integrals over a real line. We found this condition. And we would like now to describe classes of functions for which it would work. So we want to integral of, we go back, equation 5.1. So this integral. Yeah. So now we write, we want now to integrate singularities. We would like now to integrate not only integrals from minus infinity to infinity, but for example, if it has some problem in some point, yeah? So now integral from minus the alpha, beta, and this integral. Now we have this asymptotic behavior. So for large x, our function behave in this way. So for example, our function decrease as x in the degree n. So now we have our integral represented as this and this. So we see that in this case we get non-negative, we get non-infinite results. So what is conclusion? So if asymptotic behavior is 1 over xn, the function approaches 0 fast enough for our machinery. No, this was, it should be, because even in your usual course of analysis, you know that function is integrable 1 over x in the degree n when n is larger than 1. So when this function is integrable, we can apply our method. Let us consider now examples. So for example, we want to integrate this function. So it can be, you did this in your course of usual analysis without any complex analysis, without any Cauchy theorem. More or less now we would like to just support this to get the same answer by complex analysis. So typically in your course of usual analysis, you make change of variable x tangents phi, and then you get pi. Now we want, our aim is to get for training, to get the same pi, by using complex methods. So we can consider this contour. Here our function z equal plus I, because we are looking for singularities. X squared equal minus 1 has two solutions. X squared equal minus 1 has two solutions. X equal I and minus I. So there are two singularities. If we go up a way, our singularity is this point. If you go this way, our singularity is this point. Yeah. Now, if you make integral over contour, it is this integral, either of them. Yeah. So we make that this is integral of what we are looking for in the limit, and integral of this. So on this, no, there is not maybe good notation, say infinity. This is this contour when radius go to infinity. So this is, it's better right here, C R and limit R go to infinity. but okay. Yeah, so now we have this function, So it has this asymptotic because this is nothing. And if you multiply it by r, it go to 0. So our condition was for this function multiplied by radius if r is equal to 0. Here precisely we have this condition. Our function decrease in this way. Multiplied by radius is go to 0. So by previous consideration, it means that this additional integral, which is not needed for us, is go to 0. So if you apply this Cauchy theorem, then we will get this integral. Finally, we will get this integral. Now, this integral, which is equal to this, it is 2 by residue theorem. It is 2 pi I, and here is residue in the point plus I. So if you integrate here, we should find residue of this function in this point z equal I. Residue of this function in the point z equal I. So this is the pole of degree 1, because if you expand denominator, it would be z minus I, z plus I. So we multiplied by z minus I. So this disappear, and it would be this in the point I. So it would be 2i and 2, yeah, so it is pi. So it is the same answer as we expect from real analysis, So the crucial point, this function go to 0 quickly enough. Yeah. Then they can integrate other way around by going to down plane, and it's the answer is the same. Fourier exponential integrals. This is this already will be a part of the next course of Fourier analysis, but it's just for the moment we learn how we can calculate such integrals. So there is some function which we assume that it can be expanded to the complex plane, and here this exponent ikx dx. Of course, on real line, this exponent is bounded, but when we make analytical continuation, it would be fz, and here would be exponent ikz. This function would be not bounded because z has also the part which is I multiplied by y, and this I and I disappear, and it would be, so you can check that if you put instead of x, z, this function would be unbounded. Yeah. And what we do more or less the same as we did before, but so they did what I told about exponent. This is this part plus this part. Here is this r. This is the length of this half circle. And here we have this guy. And this guy would go to 0 very quickly. So finally we get that, no, this term is of no, this term does not play any role. So finally, if f is, for example, bounded, if we need that this go to 0, it's enough that f, for example, is bounded, or even any polynomial, because exponent in this degree goes quicker to 0. So yeah. Yeah, so the idea, no, the idea is that we can even don't think about anything. And for any function f, which is, for example, bounded, we can use this formula and calculate these integrals. These integrals will appear in our course on Fourier transform, and we shall use complex analysis to calculate these integrals, Now, concrete examples. For example, we want to calculate, in fact, this is what will be called Fourier transform. So we want to calculate Fourier transform of this function 1 divided by 1 plus x squared. So we know that this function is at least bounded, and this would make decreasing on the, we should use over half plane. So then we do this with usual Cauchy residual class theorem. So this integral is equal to pi I, this coefficient in the point plus I, because we won't be in half, because only in the half plane it's go to 0. Yeah, so this is equal to this. Fourier of sine and cosine integral. This is also would be in the second part of the course, so called cosine transform and sine transform. So they do this representation. This is Euler formula. From Euler formula, no, maybe it would be better consider just cosinus. If you consider cosinus, they would be plus without sigma and 2, yeah, for example. No, they try to unify in one formula cosinus and sinus. If sigma is 1, it is cosinus. If sigma, how we get sinus? In sinus, it should be it's sigma square. So I square would give us -1, and I in denominator give us I. Yeah. So now we want this. We use this formula, and finally, how we do this? This is just real part of the integral which we calculated before, and this is imaginary part I integral which we calculated before. So cosinus we get as real part and no up to I, and sinus as real part. I think this will be maybe okay. It's possible to do in the same way, and many in other integrals. Cosinus by Cauchy residual class theorem. Dirac delta symbol, it's another course, it's distribution theory. So more or less we finish technical part. We finish a technical part of the course. This is Dirac delta symbol, it's totally different course. It's course on distribution theory. Yeah, so many integrals can be calculated. Then I plan the course in the following way. Since we have two different groups, engineers and mathematicians, multi-valued functions is a difficult topic. It would be go to mathematicians. Therefore, since next week, we start the Fourier course, and I will give you more or less everything to prepare for maybe 1 week or 10 days for pre-examination and complex analysis. And then in March, I will be back to this and give 1 or 2 lectures just for mathematicians, which will be much more complicated and more mathematical. So today you will get the last home task in complex analysis. I also will send you more or less some preliminary how can look pre-examination. And since this Wednesday, we start Fourier analysis. Yeah, so this is my plan. And then we will, I hope we will have time to go back and to study complex analysis on essentially maybe 1 to lectures higher level, because multi-valued functions, branch points, and this is this is much more complicated theory. And yeah, I want to come to Riemann surfaces and so on. Yeah, so this is Okay, so it's enough for today. We finished this part of, I can say, complex analysis for engineers is finished. And we start Fourier analysis and be back to more complicated complex analysis for mathematicians, yeah. Then I checked with my colleagues. They thought that it's not good that she will have books on the exam or notes. So therefore, we do the following. I still would not ask detailed proofs. I would ask you only schematical proofs. But main formulas you should remember, for example, Cauchy integral formula, Cauchy-Riemann conditions, or be able to derive for yourself, yeah? What I can tell, how to find these residues, you should remember. There will be problems of this type, yeah. Okay, so it's enough for today. Thank you. Stop share and lecture.